Standing waves in air columns. In this session, we will explore the physics of standing waves within air columns. Our outline includes a deep dive into boundary conditions for these columns and how they differ between open pipes and those closed at one end. We will also examine the practical application of resonance in musical instruments and how environmental factors like temperature can shift the frequency of the sound produced. Standing waves in air columns are created by the interference of longitudinal sound waves traveling in opposite directions. This phenomenon is a perfect example of the waves under boundary conditions model, which we can apply to instruments such as organ pipes, flutes, or clarinets. The specific way these waves behave is determined by the boundary conditions at the ends of the pipe, which may be either open to the air or closed off by a rigid barrier. Boundary conditions are described in terms of nodes and antinodes. At a closed end, we find a displacement node because the rigid barrier physically prevents the longitudinal motion of air molecules. Interestingly, because the pressure wave is 90 degrees out of phase with the displacement wave, this closed end corresponds to a pressure antinode. Conversely, an open end acts as a displacement antinode and a pressure node. Since the pipe is open to the atmosphere, the pressure at that end remains constant at atmospheric pressure. You might wonder how a wave reflects at an open end if there is no solid wall. Reflection occurs because of a change in the character of the medium. Inside the pipe, regions of compressed air are constrained by the walls. As a compression exits the pipe, that constraint is suddenly removed, and the air is free to expand into the open atmosphere. This transition provides enough of a change to allow a portion of the sound wave to reflect back into the column. For a pipe open at both ends, both openings act as displacement antinodes. In the fundamental mode, the wave extends between these two adjacent antinodes, covering a distance of half a wavelength. We calculate the fundamental frequency by dividing the speed of sound by 2 times the length of the column. In these open pipes, the harmonic series is complete, meaning it contains all integer multiples of the fundamental frequency. To find any higher harmonic, you simply multiply the harmonic number by the fundamental frequency. Let us visualize these normal modes for a pipe open at both ends. The diagrams show that for the first harmonic, the wavelength equals twice the length of the pipe. For the second harmonic, the wavelength is equal to the length itself, and the frequency is twice the fundamental. By the third harmonic, the wavelength is 2/3 of the pipe length, and the frequency is 3 times the fundamental. In the displacement graphs, you can see the antinodes at the ends, while the pressure diagrams show nodes at the openings and antinodes in the center. When a pipe is closed at one end, the boundary conditions change significantly. The closed end is a displacement node, while the open end is a displacement antinode. The fundamental mode here extends from a node to an antinode, which covers only 1/4 of a wavelength. Consequently, the fundamental frequency is the speed of sound divided by 4 times the length. Unlike open pipes, these columns only support odd integral multiples of the fundamental frequency, meaning only the first, third, and fifth harmonics are present. Temperature plays a vital role in the pitch of musical instruments. For wind instruments like the flute, an increase in air temperature causes the speed of sound to increase, which in turn raises the frequency, making the instrument sharp. String instruments like the violin behave differently. As temperature rises, the strings thermally expand, which decreases their tension. This lower tension results in a lower frequency, causing the instrument to sound flat. This explains why musicians must constantly retune as the performance environment warms up. Resonance is the mechanism that allows musical instruments to produce loud, clear sounds. Air columns are typically excited by a source that contains a wide range of frequencies. The column then responds with large amplitude oscillations, specifically at its quantized natural frequencies. Different instruments use different excitation sources. Woodwinds often use vibrating reeds, Brass instruments rely on the vibration of the player's lips, and flutes use air rushing over an edge to create the initial sound. Let us look at a practical example involving a drainage culvert that is 1.23 meters long and open at both ends. Using a speed of sound of 343 meters per second, we find the fundamental frequency by dividing the speed by 2 times the length, which gives us 139 Hz. Since it is open at both ends, all harmonics are present. The second harmonic is 2 times the fundamental, resulting in 279 Hz. And the third harmonic is 3 times the fundamental, equaling 418 Hz. Another example involves a pipe partially submerged in water, which creates a column closed at one end by the water's surface. The water surface acts as a displacement node. In this setup, we can find the frequency of a tuning fork by adjusting the length of the air column until we hear resonance. If the first resonance occurs at a length of 0.0900 meters, the fundamental frequency is the speed of sound divided by 4 times that length, which is 953 Hz. Successive resonances for this closed-end system occur when the length equals 3/4 of the wavelength and 5/4 of the wavelength. In summary, standing waves in air columns are defined by their end conditions. Closed ends are nodes, and open ends are antinodes. Pipes open at both ends produce a full harmonic series, where the frequency equals an integer times the speed of sound divided by twice the length. Pipes closed at one end only produce odd harmonics, with the frequency equal to an odd integer times the speed of sound divided by 4 times the length. Resonance occurs when an external source matches these specific natural frequencies. To conclude, consider these review questions to test your understanding. First, think about the geometry of the waves. Why does the requirement of a node at one end and an antinode at the other limit a closed pipe to only odd harmonics? Second, reflect on the environmental effects we discussed. How does temperature specifically alter the speed of sound versus the tension of a string, and how does that change the pitch we hear? Understanding these relationships is key to mastering wave mechanics.